Hello, everyone. It's nice to see full room, even fuller than full. Before we will start, you can navigate yourself to this GitHub repository, which contains the notebook we will go through today. It's under Martin Fleiss, which is my profile, GeoPandas 1.0 and ideally, you clone it to your own laptop because it also contains some files we will be reading. And if we scroll down, there are instructions how to install the environment we will need. We recommend using Conda. If you're not friends with Conda, you don't have to. You can also pip install everything. You can try using my binder, but it may take a while to start. And you can also try running everything in Google Colab, but I'm not sure how it's going to work with the files which are loaded from the repository. We'll probably need to clone the repository into Google Colab. This workshop is meant to give you some insight on how to use GeoPandas 1.0. While writing the proposal for the workshop, we optimistically assumed that GeoPandas 1.0 will be released by now. That hasn't happened. So we are loading GeoPandas from main, from GitHub. But everything we will be going through today is stable, and we don't expect it's going to change until we release the full 1.0. So you can remember what we'll be speaking about, and don't worry that it's going to change, hopefully. We will give you a couple minutes to actually set up everything. All the instructions should be in the README, but essentially we would like you to create an environment, ensure that the latest GeoPandas from GitHub is installed in there. If you create a Conda environment, that's going to happen automatically. If you're doing pip install, you need to ensure that you are installing the latest one. And once you have all of this, we would like you to open the notebook, which is in the repository. There should be only one notebook called GeoPython 2024. And once you are ready, we are also ready. We can start going through. I will use this time for some introductions. My name is Martin Fleischmann, and Joris van den Bosche here is with me. We are two of the maintainers of GeoPandas project. Joris since 2016. I've been with GeoPandas since 2019, I think. And I'm based at Charles University in Prague, and Joris is based at Voltron Data. I'm based in Belgium. We have quite a lot of contents to go through, but we don't have to necessarily go through all of it. We would like you to ask questions even throughout the workshop. We don't want to kind of stand here, go through whole notebook, and then maybe have some time for questions and scrolling back through the notebook to the very top to answer the question relevant to that code. So if you have any question, just raise your hand. We have second microphone in here, so even people who are online can hear the question, and we will try to answer it as we go through it. Yeah, anything else? So, can you raise your hand who does not have the environment ready? Okay, so I will wait a bit. We'll wait a bit longer.
And if you run into any problem or if we can help, please, yeah, raise your hand.
Yeah, I suppose that if the full room is downloading all the packages at the same time, it may kind of take a bit, but you know, it needs to happen. If you don't have Git, which is probably required to install GeoPandas from GitHub, you may be able to use the latest alpha release, but that doesn't have everything we will be covering. But you should be fine, I suppose, with the main. GeoPandas is a pure Python package, so there is no compilation happening. All the dependencies are depending on C libraries are compiled, and you will be just pulling the wheels from PyPI or CondaForge. So it should just work, you know, as it always does with Python packaging. So let's do an update. Can you raise your hand who does not have the environment ready? Okay, it's getting better. We are nearly there. So I will just switch over to I don't see the right side. For some reason, I don't see the edge of the screen. Good, much better. Okay, if I'm gonna zoom slightly down to the code bit, is it large enough from everyone in the back row? Yeah, it looks like it is. Cool. So the final update, who is still waiting for the environment to be prepared? Only a few people. So I'm sorry, you will have to keep up with us. But I will slowly start. Is there anyone in the room who doesn't know what the GeoPandas is and would like some brief explanation? No hands, great, which means I can easily skip the explanation of what GeoPandas is, and we can go straight to the code. It's slightly random set of new things, changes, and tips on how we should be using GeoPandas now that we are reaching the milestone 1.0. Joris, please just stop me anytime when you want to add something. And I will start with one of the things that actually are changing, where we are introducing deprecations, and that's a way of getting a union of all geometries. So if you load the geometries of New York City, which look like this, we have some code for new boroughs. We have about 2,200 geometries in here. If we wanted to get a single multi-polygon covering New York, you would call property unar union, which is somewhere in here. This property is now deprecated, and there's a couple of reasons for that, and we are replacing it with a new method called union all. First reason for deprecation is that this is a fairly expensive operation. It should never have been a property in the first place. So we are fixing this kind of issue which was in GeoPandas for a very, very long time. And the second one is that we are now introducing new methods for getting the union. So the default union all will work exactly the same way as it was working before. It uses the union algorithm from Shapely or Geos. The second option is to use so-called coverage union. And coverage union is very useful for cases like this one, where we know that our geometries are not just random set of geometries, but that they form something that's called a polygonal coverage, which means that all those geometries, well, those geometries touch each other, but never overlap. Knowing this, before we send the geometries to the algorithm, can help us because we can use much faster way of doing the union. And if we compare the default, the original unary union, with the coverage, and we time it on this specific use case, we see that the difference in performance is quite significant. This also very much depends on where it's running. We've seen that on Google Colab, for some reason, the difference is much smaller. But this is sort of the difference we kind of expect in here. Just keep in mind that Shapely and Geos are not doing any checks whether the array of geometries is actually a coverage. You kind of need to know that. Some validation is coming, but it's not yet available. But if you know that this is a coverage, you can use this and make everything much faster. The same has been exposed in the dissolve function, which essentially calls union on subsets of geometries. For example, if you want to get the boundaries of different rows, we can use dissolve. And if we pass again method equals coverage, we can see that the performance will be roughly in the same ratio as before. This under the hood uses the new coverage stuff. There is much more coming regarding the coverages. If you come tomorrow for the talk on GeoPandas, you will learn a bit more on that. If you have any question at any point, please just raise your hand. There is a question in here. And
did you have the method also to dump geometries?
Hold on.
Is there a method also to dump geometries? So to dissolve geometries and then dump them into single parts?
Yeah, that would be explode, which we can just quickly have a look at that. So this gives us 4 multipolygons. And if you want to get single part, you just call explode on top of that, and you get even the indexes that get from the original one, so you can all trace it back and forth as you wish. But explode has been there for quite some time. But it has gotten faster in recent years, so worth mentioning. If there are no other questions, I will completely switch from unions and changes of the API, and I will show you how we can use a relatively recent addition to GeoPandas called sample points to create a dot density map. For that, we will read data representing some population in Chicago for 2014, slightly outdated, doesn't really matter much. But for every geometry in Chicago, which I will briefly show how it looks like, we have a count of population belonging to different socio-demographic groups. We have Asian, Black, Hispanic, White, and that's it. I think that the last column doesn't mean that. It's something else. So we have a set of geometries which look like this. And we are interested in a map which shows the composition of those geometries, but we have 4 different variables to work with. Just quite a lot to use traditional choropleth map. One way of doing that is to use dot density mapping, and The simplest way of the density mapping is essentially a choropleth map in principle, using only one of those variables. So let's start with the white population in Chicago. The way of doing that is that you usually sample points from each geometry and sample amount of points representing either the total population or 1 point per every 50 people, or in our case, 1 point for every 100 people. And GeoPandas has a new method called sample points, which does exactly that. So we are passing the series representing the number of points we want to sample from each of those geometries. And we get that number of points by dividing the number of people belonging to each group by 100 to get a reasonable number of points we can actually work with, because you can't see it if it's in thousands and thousands of points. And if you just simply plot it, and if you use the black and white, it kind of looks like one of those old textbook examples of the density mapping. And this is the spatial distribution of white population in Chicago. But we have 3 other variables. So we may want to put them also on the same map and use the sample point to get the density map, which includes all 4 of them. So we will do exactly the same. We will get points representing population of Hispanic, Black, and Asian groups. And then we can just simply use Matplotlib to plot them all on top of each other to get a the density plot, which looks like this. But given that all of these, white, Hispanic, Black, and Asian, are just geoseries, like this one, geoseries with multi-points, it's hard to get a legend on top of that. It's kind of complicated to work with that. So it may be easier to just represent that within a geodata frame. So there are many ways of doing that. The simple one for the visualization purpose is that we can just get a single multi-point per group and create a very small geodata frame containing only 4 rows, which we can then visualize using the plot method of GeoPandas. And to ensure that we use the same colors, we define our own custom listed color map from Matplotlib. We can also plot the boundary on top of that, and we get the legend essentially for free from GeoPandas. And because this is already a GeoPandas geodata frame, and we know that plot for static plotting and explore for interactive mapping are very similar in terms of their API, we can essentially do the same thing and get the interactive density plot using Leaflet.js. And now it's time for questions before I move on. Can you pass the microphone? Just we need to pass the microphone because we have people online and they wouldn't hear you.
Hello, I'm quite new to GeoPandas, but I see that you are working with the volume.
Yes.
Is there the same? Are there the same commands for IPyLeaflet or not? Or some of them?
You would probably be able to get exactly the same map with IPyLeaflet. We don't natively wrap IPyLeaflet in GeoPandas, but as soon as you have the geodata frame with points, this one, I think that IPyLeaflet should be able to do exactly the same thing as we do with Folium. We decided to wrap Folium with an Explore because it's much lighter than IPyLeaflet, and it works in more occasions than IPyLeaflet, even though IPyLeaflet is much more powerful. But there's many options to choose from when we come to interactive mapping.
Yeah, you certainly find examples online of plotting a geodata frame with IPyLeaflet.
Yeah, I'm not using IPyLeaflet myself, so I can't really explain how it's done, and we don't have it installed in the environment in here. Okay, any other questions back there? Can you wait a second? So no, it's the question of the online people. I can hear you, but they can't.
Okay. So regarding to that non-interactive map, the plot, the resolution of this bitmap and the file format where we can export this to the file, actually.
That's a question essentially on matplotlib plotting. So we can specify the size of the figure in inches, and when we are saving the plot to file, you can specify the DPI, dots per density, dots per inch density. So you can essentially control the resolution of the figure if it's going to be a raster. But you can also save exactly the same figure into PDF or SVG, which will essentially keep every single point. I'm not sure whether the output of that will work properly, because there's going to be a lot of points and they're going to be very tiny. And I know that certain rendering engines of SVG tends to have like a minimum size. So it doesn't always look as it looks right now, but you can control the resolution with matplotlib where you are essentially saving the file. So we are just plotting it here in the notebook, but normally you would have one more line. I can actually show it, probably. It's going to be easier than just talking about it. So we directly import matplotlib. And in here we can just use savefig. You go with PNG. And we specified it at 300 dots per. Yeah, and here's our file. And you can see that right now resolution is quite higher than what's visible on the screen. Okay, any other questions to dot density mapping and sampling points from geometries? If I remember correctly, no. Do you remember if the sampling works on line strings? Or maybe Levi remembers that because Levi was implementing it. Yeah, at one point we had implementation which worked on line strings, but we can essentially try it, right? Well, you can try it for yourself if you're interested, whether we can sample points along the line. I think that there was some implementation, but don't remember it any longer. Okay, yes, one more question.
Does this functionality also work with the chunk size? If I have a very big CSV file, for example?
This is expecting that the whole geodata frame is in memory. For chunking, you would require Dask GeoPandas geodata frame, and I don't think we have exposed sample points on there.
No, maybe also to clarify, like, because I know other libraries have a sample method that essentially take a subset of your sample rows from existing data, and then you could say like I have some file on disk and I just sample some rows from it. In this case, it's a different kind of sample because this creates new data. It's like it's in this case a polygon. Those polygons are what you have in memory. That's your data frame, and you essentially sample points out of the interior of the polygon. So it's creating new data. It's not sampling from existing data. It's a difference.
Yeah. Okay. I will move forward to the section on triangulation, because we have now implemented generation of Voronoi polygons and Delanoy triangulation directly from geodata frames. So assuming point geometries, in this case representing the location of grocery stores in Chicago, look like this. We can easily create a Voronoi polygons out of that. The simple method called Voronoi polygons, which gives us a set of polygons which are obviously not, well, in this case they may be aligned. I'm not certain if they aligned to the original points, but you get a set of geometries looking like this. Voronoi polygons as you know them. We can optionally return not only the polygons, but well, not necessarily the polygons, but only the edges of those polygons by specifying that we want only edges. So only edges equals true, and the result would look like that. And you can also optionally pass different extent to, if you want the resulting Voronoi tessellation to cover, for example, larger area than what the default is using, you can do that, because obviously points on the edges have their cells tending to go towards infinity. The other side of triangulation is the linear triangulation, which again creates polygons, but it uses different points as vertices of the triangulation, not as the centers and the seats of those polygons. But in principle, it works exactly the same, apart from the fact that you're not clipping this by anything, because nothing here goes to infinity. You can again get only edges out of that if we are interested only in the line work, not the polygons themselves. I'm showing it on points, but the method doesn't really care. And we can also take the example of the Chicago community areas from the dot density mapping and use those polygons, as you can see, these are polygons, as an input for either of the triangulations. And you will see that the result looks something like this. And that's because Geos under the hood extracts all the points from those geometries and uses those points as inputs. So it doesn't do something like you would maybe call polygonal tessellation. It essentially just extracts everything from there. If you want to create a tessellation based on polygons and treat all those polygons as individual seeds, so instead of their individual points, the polygons or lines themselves, we have built implementation on top of the Voronoi polygons in GeoPandas/Shapely into the libpython package, but I'm not going to cover it today. You can look it up yourself. There's a link in the notebook for that. It's an extension. And if you want to look into the reason why this tessellation is so dense, we can use another new method called extract unique points, which gives us all the points representing each of the geometries in the data frame. So we can then see that the reason why the tessellation above looks the way it looks is because the edges of these geometries are very, very densely populated by points. It tends to be very detailed to a degree, even though it's mostly rectangles. Looking for hands, for questions. There are no questions. There's two questions on the side.
Do you already support 3D points for triangulation, so with a z-index?
Nope. Essentially, as with everything in GeoPandas/Shapely/Geos, which is what is doing all the operations, third dimension being be it z or m, is usually maybe carried around, but never taken into account. And there are no plans of changing that.
Yeah, there are only a few methods in Shapely Geos that will where you like interpolate. If you interpolate between 2 points, it will also interpolate the z coordinates. But whenever you do any actual operation like intersection or do they like or clipping or overlay, it always ignores the dimensions.
Yeah, there's another question.
For the Voronoi, I was wondering, is there also a possibility to return the input data enriched with the Voronoi polygons?
No, we don't expose that because essentially you have the input data in the first place, right? That's what you are passing in. I don't remember exactly how it currently works with the sorting, because I remember I was making a pull request to Shapely to ensure that we allow the output to be in the same order as input, which is not the default. And I don't know whether it all went through. I don't think so. So it's possible that currently we don't necessarily match one-to-one. So you would need to do S-join, spatial join, to actually get the proper order if you want to pass the information from one to the other. That's what we do in the libpython implementation, which is built on top of that. That's what that I remember. But otherwise, no. And I don't think Geos can actually return it. So Geos also assumes that you know what you're passing in and doesn't return the input. I think not even optionally.
Yeah, it's certainly a good feature request.
Yeah.
Though.
Yeah, like once we ensure that Shapely support the ordered output, we will probably try to ensure that it's always coming from GeoPandas, so you can align rows one-to-one. Yeah. Maybe something for GeoPandas 1.1. All right. Quite often you start with linear geometries, line strings, linear rings, multi-line strings, which essentially enclose certain areas. They would form polygons, and you need to extract those polygons out of those. For that, we have currently implemented a method called polygonize. So if you, for example, take the edges from the Voronoi triangulation we just generated above, and we want to get those actual polygons, kind of assuming right now that we cannot get them directly. Let's assume that those are street networks, for example, or something. You can directly call polygonize, and that does all the hard work for you, and returns a polygon for every area which is from all sides represented by the given line work. Doesn't matter if it's a single line enclosing the whole thing, or if it's composed of 20 lines intersecting each other, you will always get the area back. There's analogous method called build area, which has slightly different purpose, and it tries to take the line work, which is in your geoseries, and build a single areal geometry out of that. So if we use exactly the same input into the build area, we see that we get only one geometry. That sounds kind of strange, right? But the reason why this looks strange is because the build area implicitly assumes that there are certain features in the data that are representing holes in the polygon. So we can add some holes into that as 1,000 feet buffers around the locations of groceries we used above. So we will get a line work which looks like this. We have the edges of the triangulation, and now we have some buffers around the points. And if you use the build area right now on this, we see that we have holes, and if there are some buffers which were outside of what could kind of polygonized, could turn into a polygon, we have new geometries in here. If I use polygonize on exactly the same input, you will see that it's very different, and that we have polygons within each enclosing area and their intersections. Expecting questions?
I think in the latest Geos releases, they implemented a fix for having bad intersecting geometry strings. I think in PostGIS they already implemented it, that if you have a lot of complex lines like this and you polygonize, most of the time it doesn't work because it can't make the connection points. Is this fix also implemented in GeoPandas?
If it has been implemented in Geos, then it's going to come through Shapely essentially without our involvement. If it's the fix of the actual Geos algorithm, if it doesn't require any new keywords or anything. I'm not entirely sure about this one, but normally fixes in Geos we get essentially for free. Yeah. Okay. And the last thing from me before I will pass microphone over to Joris is the method called segmentize. Because if we, for example, extract the unique points from the result of the Voronoi triangulation, we get this set of points, which doesn't very much resemble what the triangulation looked like. But we can make it so. We can ensure that along the edges of those original polygonal geometries, we include additional points which are no further than a specified segment length from each other. The algorithm tries to get those points as close to this distance from each other, but obviously we kind of need to interpolate into a distance which is not necessarily divisible by 1000. So it's maximum segment length. And then if we get the points out of that, we see that the result very much resembles the original input of original polygons. And then it obviously depends what you want to do with these kind of things and whether it's useful or not. For a lot of geometrical operations on polygons, you don't want to segmentize because you're adding more information where you don't need it. But if you are expecting that you are taking your polygons and turning them into a point representation or coordinates representation, then you may want to do segmentation before that. Unless there are any questions on this, there's one.
Hi, I'm wondering why you chose to call this segmentize, because I would expect that the output would actually be like short line segments rather than the points that separate the segments.
They are. So, but it's hard to visualize that. So after I call segmentize, I get back polygons again. But if I plot those polygons, I don't see that there's more segments representing that polygon. So let me do something else. So the original Voronoi, we can plot both on top of each other. You can see that every single polygon in here is represented by 4 vertices. Once I do the segmentize, this is no longer the case. And this is also one of the new methods in GeoPandas 1.0. You can see that every single of them is represented by a much higher number, depending on their original size. But we now know that all those vertices are always closer to each other than 1,000 feet, which is what we have specified in here. Saying feet because the original data frame is in feet. And if we plot both on top of each other, so, and the polygons. It didn't work. This should have worked differently than it does. I think so. You know what always happens when doing live workshops? You find bugs in your own code. So the other order it worked. So right now what we have here is that we see the geometries and the location of vertices representing them after we use the segmentize. So if I wasn't including the points on top of this, we wouldn't see the difference. But internally the vertices and the edges are represented slightly differently in more granular way. Yeah, so we see that we have between 2 times higher the number until more than 20 times, depending on the size. And I'm curious what Joris is trying to do in here. Go on.
Yeah, that was just to show the original data. Like, we do exactly the same this time. Like, we plot a polygon and plot separately the how the polygon is built up, like its vertices. And here you see it's very simple polygons. They just each time have their corner points as points. So that's the main thing. Like the segmentize still returns you the polygon, just with more points. Every segment, every line part of the polygon has been segmentized into multiple segments. That's should make it easier to visualize that. Yeah, I think so. In general, if you ask why is it named a certain way, the answer is often because PostGIS. We most of the time take the same name if it already exists there. I think actually Geos called it Densify. But then we took the PostGIS name to be consistent with that, because that's what people know and not the method in Geos. But yeah. Okay, any more questions about these parts? Then a next section where I continue is Hilbert distance. So that's the Hilbert distance itself is not like new from 1.0. I think it already existed in one of the latest releases. But so this is related to sorting geometries. So until recently, if you were sorting a data frame or you were sorting on like a geo series, it would give an error like I can't sort geometries. Nowadays, we do support sorting geometries, and that's using the Hilbert distance method under the hood. I will directly explain that a bit in more detail. But so the data to show it with is those dense points that we just created in the segmentized section above and extracting the unique points. So I converted to a data frame, and let me plot them. But the way that I plot them, I give them a color, but just like color them based on the order in the data frame. So I created the quantile label. If you look at it, it's just some numbers from 0 to 100 and then repeated enough so that's the length of the data frame. So you can see the color here represents the order in the data frame. So there is clearly already some order that's from the way that we created the data set in this case with the triangles and then the segmentize. But it's certainly not necessarily like, sorted in a deterministic way. And let's see, that also means that if you would chunk your data frame, and that's something that will come in an example application after this one, if you chunk your data frame, so in this case we dissolve by the quantile label, so we essentially just cut our data set into 10 pieces, just consecutive the order of the data frame, cut it into 10 pieces, dissolved it, so take the union of each of those 10 pieces, get the bounding box, the envelope, and then so we see a bit the envelopes of the bounding boxes of like how we cut it into pieces. Sorry, not 10 pieces, 100 pieces, to be clear. That's just to illustrate the current order. So something that is new is that you can now sort the data frame by specifying the geometry column. So we will get some spatially sorted data frame. And if you then show the same thing, you will see now that there is a different order, and this will be it's a deterministic order, so you can actually have a fixed order of your data frame if you sort it. The way that it works is using the Hilbert curve under the hood. So in general, sorting spatial data, there are multiple ways that you can do it. Typically, it's based on some space filling curve. So you're in a 2D space and you need to determine somehow what's the order. How do we divide that 2D space into something linear so you can sort it? There are different ways that you can fill a 2D space with some curve. Hilbert curve is one of them, and you see it a little bit in this example. So if you Google Hilbert curve, you will see like how it fills a space, but it starts bottom left, and then goes up and goes down again. And in general, this tries to maximize for every point, for every 2 points, if they are close together spatially, that they are also close together on the curve. Of course, that's not possible for every point, because here, for example, you have 2 points close to each other, which will be very far apart on the curve, but that's the constraint of a 2D space. So that's the Hilbert curve. You can also, there is a method that just calculates the number, but what sort values does, if you sort the data frame on the geometry column, it will calculate the distance along that curve and then sort based on those integer values. One application of sorting geometries spatially is to ensure that the way that we now, so I again took like for the 100 pieces how I chunked my data frame, dissolved like to the union, take the envelope, and you can see now that the data, the different bounding boxes of my chunks in my data set, they are much less overlapping than what we had before. Like what you see here compared to what you see here. So there, the different chunks in my data frame are better separated. And one of the applications of this is if you need to select some data, you only need to work either by selecting manually, or you have some operation that has to, for example, only look at those rows or those geometries that might intersect. You will be able to have a smaller subset of your data that you need to select to get all the data that are in a certain area. So you can optimize getting subsets of your data based on the where in your study area you are. So that's it's also something that, for example, in the we have a parallel version of GeoPandas together with Dask, can make use of that when optimizing a spatial drone algorithm. But the application that we have here in the notebook is loading from a file. In this case, we are using the parquet file format. And if you know I only need to read a small subset of my data, and I mean subset like spatial subset, like with the bounding box, we can optimize doing that by having sorted data. I have a small example here. This is already a little bit a bigger data set available in the GeoDatasets package from Geoda. It's all the, it's a polygon data set covering the US with some health data. Just for the purpose of seeing some difference, I took it times 10, the number of rows. So now we have 700,000, a bit more than 700,000 rows. I'm writing into Parquet. I'm also adding here the row group size because because Parquet, when reading a Parquet file, the row groups are essentially how the Parquet file format internally is chunked. And it can avoid loading a whole chunk. But for this example, our row groups or chunks in the file format need to be small enough to see the difference. If you have bigger data, actual big data, then the default is fine. It's just for this example, I needed that to show the difference. So I now have a Parquet file with 700,000 polygons, and I can read the whole data set using read Parquet. Takes around 1.5 seconds. But let's say that now we want to only, when reading, we want to filter based on a certain bounding box. So by default, the Parquet file format, or the current way that it's implemented in GeoPandas, it has no spatial filtering ability, like you can do with some other file formats through GDAL, like GeoPackage or Shapefile. They already support that, but it was not yet available in Parquet. But with the latest version, both of GeoPandas and the upcoming 1.1 specification of GeoParquet, there is a concept of that you can write covering a column with essentially the bounding box information of every row. It's additional data that you write to the file, so it's always a trade-off, of course, whether it's worth it for your use case. So I'm going to write a second Parquet file, but now I'm saying I want to write this bounding box information to my file, so I can use that when reading. I can still read the whole file, That's the same. It should be the same as what I had above. Yeah, some variability on my laptop. So we have read all our 700,000 rows in 1.5 seconds. Let's say that I just want all the polygons that are inside the county of Bronx in New York. I take the total bounds of those rows, so I can use that as the bounding box, just to define some bounding box. And let's now see. So this only loads a small subset, so only 4,000 rows of the 700,000, and it does that in quite some less time, so a bit more than 200 milliseconds. So without any sorting, just by having that bounding box information in the parquet file, the reason that it's already faster is that while it probably still needs to load the whole parquet file into memory, because it's not spatially sorted, the filtering can already be done on, like, before actually converting the data to pandas, parsing the well-known binary, because that's how those polygons were written to parquet, parse those well-known binary into shapely objects. So you avoid all that work, and that's the reason that it's already quite a bit faster. Without what I actually want to show now is that if we can ensure that our file is, the data in our file is actually sorted spatially, to ensure that those bounding boxes, as I showed in the previous example, that the bounding boxes are less overlapping in the data. So sorting the data, I have my sorted version, writing the sorted version to parquet as well with the bounding box column. And I can now read the same. And you see I have exactly the same number of rows with the same bounding box that I specified, but it's still like a bit less than 10 times faster than the version without where the data was not spatially sorted. Just to illustrate, or maybe are there any questions about this? No questions yet. What I wanted to illustrate is that this bounding box information is essentially, if you read I'm importing pyogrio to read the parquet file directly to see the raw parquet data. So there are a bunch of columns. There is a geometry column, but essentially in the data file there is an additional column which is called bbox. That's just the default name that we use, which has 4 child, so it's a nested column where you have the 4 numbers that you need to define a bounding box: xmin, ymin, xmax, ymax. So it will write that information to the file. It will use that information when loading, and you specify a filter. But we don't actually read that data when reading. So we drop that information. If I actually show the data itself, so the last column here is just our geometry column. So we drop this bounding box column because you essentially, we assume that by default you only need it to improve your reading performance. Okay. No questions? There is a question.
Is there a fallback when I already have a bbox column?
The thing is that at the moment the implementation is like this, that we calculate it while writing. We don't, but it's a good question. We could allow, that you already calculated up front, but the thing is that we need to write information about the presence of that column into the metadata of the parquet file. because that's if you then like read it with, for example, with GDAL or in QGIS or some other system that supports GeoParquet files, they will look into the metadata of the file to know whether there is a column that represents the bounding boxes. So yeah, we need, like, it's not just columns that are present already, we need to know about it to write that metadata. Can you give it back?
What I mean is, if you already have a bounding box column with the B box name, but it represents some other data, will you overwrite it? So if
we will by the time of the final release, we will raise an error that you can't do that. Like, then the solution will, if you want to make use of this column, you will have to rename your existing bounding box column. But in theory, the specification of GeoParquet allows that column to have any name. But yeah, for now we didn't provide that flexibility from GeoPandas. Okay. Let's continue with another topic, distance-related topic. That's the distance within. So that's something actually new from 1.0, I think. Or yeah. So we already added a distance within method on, like, just on a series that already existed for a few releases, where you essentially, for every geometry in your series, you want to check, is it within a certain distance of another geometry? The typical, like, or certainly something that I have done in the past is, like, I calculate if I have, for example, points, and I want to know if they're within a distance of other geometries. Like, I take a buffer and then check whether the other geometry is intersecting that buffer. But the specific, like, the distance within specific methods is a lot more efficient than manually calculating a buffer and then doing an operation with that buffer. If all you need to know is it within the distance or not? What we already had was just a method on the geoseries element-wise, like, for every element in my geoseries, is it within the distance of some other element? The thing that we added to 1.0 is that you can now also use this predicate, this distance within predicate, in a spatial join directly. So for that example, we have two new data sets. One data set are points of abandoned car locations in Chicago. So both point data sets. And the other data set that we are going to use are the data set we already used before, which are the groceries. So locations of groceries in the same city, which are also points. Yeah, I assume they're just points. I don't know why multi-point, probably from the way that it was read in, but we have 2 times point locations. That's what I already did. So we have these are the car locations, and let's say that we want to know for all the cars that are within a certain distance of a grocery, but not just is it within a certain distance of a grocery, but also, like, which groceries. And that's what a spatial join does, because it's not like you actually join information of the 2 data sets. Like, we have all our car points, and we want to match it with every grocery within, in this case, a distance of 1,000 meters around that point. And that's what if you specify the D within predicate to spatial join does for us. So we still have here all our points from the cars data sets, but we added information about different groceries. This will also mean that very often you will have multiple groceries within a distance of 1k around the point. And I think you can see it if I show the first 20. So in that case, you will, for example, here, you will see that like we have one point that is repeated twice because it was matched to two groceries that were within 1k of the point. So this makes it, a bit easier to do this kind of predicate, like the spatial join. All the other predicates, you need an actual intersection or touching or within. But here it allows like a different way of joining. And it is just showing the resulting, all the abandoned cars that were within a certain distance of a grocery shop. So the example here was showing specifically the spatial join, where you can use the distance within directly inside. Where is my focus? But as I mentioned, so a geo series also has a distance within methods, so that works element-wise. And in addition, if you have a geoseries, there is also the spatial index attribute, and you can use the query if you want to know. You don't want to make the actual join between the two data frames, but you just want to know all the combinations of indices into my original series and indices into the other data frame of all the matches, all the two set of points that are within a certain distance of each other. You can use the query method of our spatial index, where you can pass this distance within predicate as well. Okay, that's about the distance within. Then a question. Yeah.
So this works with two sets of points. Does it also work with if I have a set of points with lines, like give me lines that are in within, let's say, 1 kilometer? Yeah. It's essentially what it does. It uses the distance, like if you would calculate the distance between two geometries, it's using that. So if you have like the distance method itself also works on any kind of geometry. There are a few different ways to calculate the distance between two geometries. We actually show some examples later, but the distance within is using the default distance, which is just the shortest distance. Perfect, thank you.
Any other questions on the question on distance within? Question there.
So the way that the labels of the supermarket chains are clustered, you've got multiple assigned to the same color. Is that intentional, or is that?
I have an answer for this. When using the categorical plots, I think that export defaults to matplotlib's tab 20 color map, which has 20 colors, and then it gets repeated.
Yeah, that's one of the things where we're saying it before today, that plotting categorical data in GeoPandas is really like, there is room for improvement, as you can see. So if anyone is interested in contributing better to categorical plotting, that's certainly welcome. Okay, some other distance-related operations.
This is not necessarily new from 1.0. What I'm going to show a little bit later is the, like nearest distance. That already exists for some time, but it's still a very relatively new and very useful method to show. So what I have here is two data sets. So homes, we have, I'm not entirely sure the location, like which city it's about, but it's point locations for some homes. And we have food establishments, so I assume that will also be points. So we have houses, we have like food establishments, and we want to know, for example, for every home location, what's the nearest food establishment where you can go eat something. You want to know, so the pairwise distances between those two. Maybe you're interested in only the nearest. I will show that directly. Or you might want to know all the distances, all pairwise distances. That's a much more expensive operation. It also it can quickly. It depends on the size of your data because it blows up, of course, with the size of your data. So it's not always realistic to do all pairwise distances. But there are also still, and that's what we wanted to show here, better ways and worse ways to do the same thing. So in general, when you did in the past, methods using apply in GeoPandas, there are nowadays with all the functionality that has been added the last year, often ways to do things better. Without having to do apply, which is essentially a for loop under the hood. So here for just a small subset of the data, we are getting manually calculating using the distance methods, for the first 1,000 homes, I calculate the distance to from the other data set and the food establishment to that one point of the homes. But so here there is a lot of overhead because we are calculating the distance on the point geometries of Shapely. And as long as you just have points and you want to calculate distances, it's actually more efficient to do that outside of Shapely. This is another way to show the same thing. It's only it's only slightly faster because that's still essentially just a limitation of the current having a full geometry is a bit of overhead just to calculate distance between coordinates. And so that's the reason that we also put in here, if you actually want to calculate brute force lots of distances, get the coordinates out of GeoPandas. And so we have a get coordinates function now, which gives you, we can check it here, you will now have a NumPy, or in this case it's still a data frame, but NumPy array under the hood with just the numbers. And then you can use either directly, you could just with NumPy do the calculation yourself, or in SciPy there is some helper function that will do this for you, these pairwise distances. You can do the same with NumPy with some broadcasting, fancy broadcasting. But you can see that it's 10 times faster just for calculating exactly the same thing. So that's the main message here. If you want to calculate lots of distances, get the coordinates out and do it yourself. Yeah.
I have a question. If I can have points in or coordinates in northern and southern hemisphere as well, because I run into some troubles calculating distances on an array, which contained coordinates in Australia and in Europe.
So for now, GeoPandas just assumes that the data that you have is like a flat, the Earth is flat, essentially, for GeoPandas, which is a reasonable assumption for many use cases, certainly when you have like your study area is a bit smaller, but if you have data covering the whole world, yeah, that's not, everything that is related to distance in GeoPandas will be somewhat wrong. That's already a first thing. So you can, of course, reproject to some also global projection that might optimize, might be the best option for distances, but like in general, if you actually have data covering the whole globe and you want to calculate distances, there are some other libraries that do that, but it's not very well integrated into GeoPandas that actually calculate the distance on the globe. But yeah, GeoPandas is planar data, and so everything is just like Cartesian distance on XY. Another question there.
Are you planning on integrating it also in or task GeoPandas to have like a parallel apply, something like that?
So for most of the methods that are inside GeoPandas itself, there is a version in Task GeoPandas. It's lagging a bit behind. I think it's matching like the last release of GeoPandas, and all the new methods that were added in the 1.0 release of GeoPandas are not yet all in Task GeoPandas. But in general, whenever there is something in GeoPandas, there will be an equivalent in Task GeoPandas that does things in parallel. There is also a more generic, like if you do some apply, there is also a generic like map partition in Dask where you want to say like, I have my own operation that works on a single data frame, like a geodata frame. I now want to do that on every chunk in my chunk data frame and run that in parallel. That works as well. But in general, that works like if your operation runs on a single chunk, not like row by row. That will also have like a lot of overhead. Okay. The second thing here in this section that I want to show is that often you don't need to have all pairwise distances. You might be interested in just the nearest. And in that case, there are actually some nice functionality in GeoPandas, making use of Shapely, that makes this very efficient. So again, like what you might have done in the past, and that is very slow, is we do exactly the same. Like we do the brute force calculation and then take the minimum to know like what's the location of the minimum. But that's, yeah, again, not very efficient. So I'm doing it here for only the first 1,000 rows. It takes, again, 1.5 seconds. Yeah, here's another example of how you could do this in the past, where you have a function that calculates the nearest point, and then that's a function from Shapely, and then calculate the distance between the nearest point that you found and the point that you have it, that you're calculating it for, and then apply that function on every element of the homes data set. Again, I needed to import this. That's a bit faster because the nearest point helps here to not have to calculate the distance to every point. But essentially, don't use this. There is now a method in GeoPandas for a bit more than a year, which is the spatial join nearest, which will, yeah, not join on an exact predicate, but will join on the nearest data set. And you can see here that we actually do this now for the whole data sets, not just for the homes. So originally it was 20,000 rows, and I was only do it for 1,000 rows, like 1/20th of the data set, and it was taking 1.5 seconds here, brute force, or here a bit faster, 300 milliseconds. But we can do this in even less time for the full data set. The reason that this is fast is because it uses a spatial index, an STR3 spatial index under the hood. It builds up an index on the points, so it can much more easily, much more efficiently find the closest point and just calculate the distance for those points. This S-join nearest is actually doing the spatial join. So it's doing more than just calculating the distances. It's actually joining the homes points with the in this case we just selected the geometry of the food establishment, so we only see the index here and then the distance. If you don't need the join but just want to know like what are the indices of my closest points or what's the distance, you can use and that's what the spatial join is using under the hood. You can use this the spatial index method directly, and then you get you get access to the distances, and then the indices are indices into the first row are the indices into the one data set, and the indices into the other data set with the matching nearest points in both.
I have the same question as before. Can you use spatial join on lines or polylines?
Yeah. So all this, like the also near, like for the spatial join nearest here, the same works. Whatever, like polygons, lines, points. The points example is the easiest because that's the easiest to think about, and that's also the case where you can somewhat like do it like the pairwise distances using like getting the coordinates and do it yourself is like the easiest case. But the distance method in GeoPandas and like in Shapely, that works for any type of geometry. I'm just checking here. And this is related to, and actually an example of what I showed before. So the nearest, spatial join nearest, or the spatial index nearest methods, only the nearest point. If there are actually 2 points that are equally, the closest points are multiple points, you can ask, like return all of them, or just return one. I don't know if it's deterministic then which one, the first one it encounters, I suppose, but not entirely sure. But so this is for just the nearest. If you want to know, like, okay, I want to know all the points that are somewhat near, like within a certain radius, then we essentially have that distance within that I just showed before. And so here's an example of what I mentioned, that you can use the query of my spatial index to then say I want to query for my, like those matching geometries in both the food dataset and the homes dataset where they're within 5 kilometers from each other. And again, you can ask, I'm not sure, in this case we can't directly return the distance, I think. No, we can. We need to update this example. That's newer, because this example was, what this example is doing here, I will run it so I can show the output, is we calculate the indices of the left and the right data set where we have a match being within 5K of each other. And then the indices are like, integer indices into my left and right data sets. And what we then did was we select based on those indices, like positionally, we select the rows of the left data set and the right data set, and we calculate like manually the distance now for those two. But I'm not sure. No, so this is still just, of course, that the distance that you specify. It's not like in the case of nearest. Here, the nearest method, there is a return distance option. Whether if you want to query like multiple within a certain distance, there is no return distance. So in that case, you actually need to do as we have it here. Like you can check like what are my matching geometries, and then you can calculate the distance. But of course, what we have seen before is that you could also do this directly with the spatial join if you want to actually join the data sets. This is an example of the like lower level functionality if you just need the distances and the indices. Okay. A question.
Does the spatial sort have impact on the speed of these distance functions?
I don't think so. I don't see a reason why would it have an impact, because under the hood the S-index is sorted as a R tree, so sortile recursing tree, and it essentially does the kind of logic of spatial sorting by itself.
Yeah. It might be, and I think I've seen an issue about it, whether it's faster to construct the index if your data is already sorted, or that you can like somehow influence that. But in any case, in all those operations, the construction of the tree with geos, like the str tree, is very fast, and the actual querying takes more time than building the tree. So even if it would optimize the building of the tree a little bit, it's still like the querying is more significant in time than the building of the tree. Any other question? I will maybe switch to this because it's still related to distance. So I was like mentioning like there is the default distance method that just short the distance, considering like the just Cartesian shorter distance on a plane. There are a few other distance methods, or like different ways to calculate the distance between two geometries that do something different for lines and polygons. So for points, that's all the same because there is just like the distance between those 2 points. But if you have 2 polygons, for example, like what's the distance between those two? In that case, there are 2 other distance metrics that are available in Shapely and that are now also directly available on the in GeoPandas. So here we are loading a different data set because we can't show it with points, but we'll load a data set of rivers, and so it's the few rivers in Europe, and we calculate a second data set, and we have something to calculate the distance to by simplifying our rivers. And so the simplify method is a way to reduce the number of vertices. I can zoom in on a single one. So you see here we have a more like precise line, and then we simplify it, so we reduce the number of coordinates in our line, and now we can calculate the distance between those two lines, for example. If you would just do distance, it would most likely give 0, because I assume that the first point, for example, here, it's the same point, and the distance between two lines will be the shortest distance. And in this case, since there is an intersection here, like an overlapping vertex of the line, it will just give 0. So those two other distance methods, which is the Hausdorff and the Frechet distance, are distances between lines and polygons that are not just the shortest. So in case of the Hausdorff distance, it's the longest distance between two possible points. So 1 point from the left geometry, 1 point from the right geometry, and then the longest, the 2 points that are farthest away from each other on those two geometries, the distance between that's the Hausdorff distance. And the Frechet distance is a bit differently. It's also a kind of the longest distance, if you have two lines, we can maybe draw, we can make use of one of those colors here. So if you have one line like that, and then another line like that, what the Frechet distance does, if my understanding is good, because I'm also not actually using it in practice, but so you start, so it has a direction, you start at the beginning, and you look at, while going through the two lines, essentially if you follow the order, like what is the line where you can fit everything inside? Like if you have 2 points that follow along the curve, like at some point here they are the farthest away from each other. In all the other cases, you can find a point that is closer, like that. So the Frechet distance will, when traversing, like with a point on each line, and you always try to look for the shortest distance between the two lines, but at some point your shortest distance at every time will at some point be the furthest away from each other, so that distance, that's the Frechet distance. So you're looking for constantly the shortest distance and then the maximum of those shortest distances.
Wikipedia uses very nice explanation. Assume that you are walking with a dog is on a leash.
Yeah.
If you're walking this route, and your dog is walking this route, the Frechet distance is the distance of the leash you require to allow this.
But so in general, those two distances are used, for example, I think it's also mentioned there, for example, as some metric for similarity between two geometries. And that's the example we also have. So I have we had the rivers and we calculated a simplification of those rivers. So we can now use one of those distances as the similarity between the original river and the simplified river. And the idea is also that the more you simplify, the less similar those two lines will become. And so the bigger the distance. And so you can calculate it for a single, for the rivers and the simplified rivers, this Frechet distance. But we then do it for a few different, the simplify here has a tolerance, and the higher the value, the coarser the results will become. And so you can indeed see that, the distance, so the lines become less similar as long while we simplify them more. So that's a small illustration of using here the Frechet distance for the similarity of the two lines. Yeah, in this case, for lines, I think the Frechet distance is more informative, certainly in this case, because we start with a line, we simplify it, and we really want to consider it as like a line, like Frechet distance will not consider the order of your points that create the line. Doesn't matter for the Hausdorff distance. While for the Frechet distance, it really follows the curve of your line. Yeah, a question.
I was just wondering, so is this actually considering the line as a line, or is this comparing the points, the vertices of the line? So can this distance happen in between two vertices of a line?
Yeah, it's not only considering the points. As far as I know, in general, distance considers, like, also if you have like a polygon, like, just let's say you have a polygon like this, and you have a point here, the shortest distance, like if you call the distance methods, it's not the shortest one of the coordinate pairs, but will be here. That's for the general distance method, and as far as I know, it's the same for the other, or not?
It is not.
It's not. So it was a good question.
Both Frechet and Hausdorff distance use only the actual vertices, and both of them have a keyword called densify, which is Boolean, and if we use densify equals true, then Geos will automatically add additional points along the line to use them in the computation.
Yeah, I wanted to mention it's a good use case of segmentize, but so you don't need it because there is a keyword that does that for you. Okay, the remaining time that we have. If you have any questions in general about GeoPandas, also feel free to ask. I will scroll a little bit back just to mention just mentioning that they exist now. If you have geometries where you might read them from some data set and they have a third dimension, but you don't care about that, or you don't need it, you can now more easily force all your geometries to be 2D or force all of them to be 3D to have consistency or to convert from one to the other. So in this case, for example, the Chicago polygons, so I suppose counties, none of them have a Z coordinate. We can force them to be 3D, and then the default is that the Z dimension gets filled in as 0. You can specify which value you want to use to fill in, but that's all it does. And so now you see that it's like a polygon Z here, so with the third dimension, the zeros here. Now it has, all of them have, if you ask, do they have a Z dimension? Yes, they all have that. And then in case so here that's an example that you can, not that this example makes any actual sense, but we could, for example, just based on the order of the rows in our data set, add a Z dimension that constantly increases. In this case, of course, it's just a toy example. And then forced 2D is the other way around. If you have coordinates with potentially a third or fourth dimension, just remove that and only give me 2D. So that's just to mention that those forced 2D, 3D now exists, and they're relatively recently in Shapely and now also added to GeoPandas. A general thing that for the remainder of this notebook, are not necessarily new methods in GeoPandas, like a lot of the things that we have shown above are like actual new methods, like to calculate certain like those distance methods. They are really new. There are also a whole patterns that people have been using for many years, because that was at some point the best way to do something, but that have been improved over the last years. And a general pattern is whenever you do something in a loop, or you apply something, or essentially a Python loop, especially with the release of Shapely 2.0 last year and the use of Shapely, all those new functionality from Shapely in GeoPandas that have been added to GeoPandas over the last year. Like most of the things where in the past you might have done something for every geometry, you will in many cases now find a method existing in GeoPandas that does that all. One, it's easier to do it in just a single go for you, and it will also be a lot faster. And so the remainder here of the notebook includes some examples where it was very typical, like a very typical use case to do it more manually in the past. For example, creating points from coordinates. If you have a bunch of XY longitude, latitude coordinates, and Shapely has a point object, and you can pass an X and Y coordinate to that point object, so you can loop through those values, create those point objects, and like whether you do that with an apply, or in this case we are mapping the point function to zipping the longitude latitude, essentially different ways, either with a map, or you could do it like with a more explicit for loop, but essentially calling the point constructor of Shapely directly. So you can see all of them take like almost 400 milliseconds. Or with an apply, that's even a lot slower, I think. Different ways to create point objects. But nowadays, we have in GeoPandas a from XY. There is also potentially a third dimension that you can pass, but the name is from XY. And so you pass all your X coordinates, all your Y coordinates, and it does exactly the same, just in like a fraction of the time. And it's also easier to use. In this case, I pass the NumPy arrays, or I could pass the, this is a method from XY is a method on GeoSeries. There are also top level points from XY that already is a bit older, but essentially you can use the GeoSeries from XY. That's for points. Another typical example is where you load some data from a non-spatial file format, and you have like the data, the geometry data, either as well-known text or well-known binary, and you want to convert that to GeoPandas. Same pattern there is that in the past it was Shapely had a well-known text module with the loads function, which was like similar as like the I think it matches the API of the JSON module in the standard library, where you have a load and a loads directly loading, like parsing a string. And so again, what you could do is apply this well-known text.loads to every element in your data set. So here, this is text. So you can see it's not geometry, it's an object, it's text. So we could apply this, or we could again do a for loop, any of the methods that I showed before. But also now there is a from well-known text class method on GeoSeries, where you can pass your column or array of texts, well-known text data, and again, it will be a lot faster, like in this case, more than 10 times faster, and also you don't need to do an apply. And again, so now we have our geometry data type, and finally the same for bytes. So if you would read some data, or you get data from, like, and you did manually some PostGIS or some other file format that uses well-known binary data. Shapely did have a well-known binary .loads function, and exactly the same pattern here. We can actually use a from well-known binary method where we pass our column with well-known binary data, and it's also quite a bit faster. So that's yeah, a few examples of methods to create data where it was done a lot to iterate over values. For well-known binary and well-known text, I showed the from methods to load data into GeoData frame. We also have the reverse to export the data, export your data frame to data frame with like the same attribute columns, but using well-known text for your geometry column. And that's like 2 well-known texts, 2 well-known binary. So that's the reverse. That's for simple cases like points, well-known text, well-known binary. There is an example here as well where you might have a bunch of points that you want to convert into lines. So the points are still in, you just have longitude and latitude. But for example, you have trajectories, and the way that it's stored in the data is because you have a trajectory ID, and essentially like every row that has the same ID number here is like a next point of your line. And what you want to do is you want to, or potentially if you want to use the GeoPandas functionality, you want to, for each trajectory, so for each set of rows that belongs together as one trajectory, you want to create a line string. Again, you could do this quite manually, like you loop over the different unique values in the trajectory, or for example with the group I in pandas, and then for each group you convert those to a line string, and so that's what is on here, like you group by and then you apply by calling the line string on the resulting values. Also here nowadays, yeah, that's yet another way. First creating the points and then doing the group by, that's just a small variation. But also here, if you have something like this with coordinates and indices, the Shapely line strings function. So this is not exposed in GeoPandas because it's a bit more like special case code that we didn't provide out of the box. But everything that GeoPandas does that is based on Shapely, you can always use Shapely directly. And Shapely in this case has a line strings function. I want to have the help of line strings. So create an array of line strings and you pass coordinates as inputs, but it also has an optional indices method here where you can specify the indices of yeah, essentially our trajectory IDs, so that the points with the same index value are used to create one line. And essentially, so we can we pass our X and Y coordinates, and then we also pass the trajectory ID to the indices keyword arguments, and that creates our line strings. Yeah, and then the final example here is if your trajectory IDs are not like numbers that start from 0, because of course there is no guarantee that that's the case. This indices argument of Shapely only works if it's really like an index into the array, or like in the resulting array, like it expects that your values start at 0. There is one more example here where we convert any value, like as long as whatever is the same value in trajectory ID will be converted to the same value using this factorize, but using integer numbers that start from 0. So then also your trajectory ID doesn't even need to be an integer. It can also be like a string identifier, but this pandas factorize will convert that to integer numbers, and essentially all we need to know is whether the value was equal to pass it to the shapely function. So that's a small extension on that. Get coordinates is something we already have seen. Also, yeah, if there are more questions, feel free to ask. Otherwise, I will just going to check. Yeah, I can finish with the last piece here. We already have seen. Just checking that I have, yeah, the correct data frame. So the get coordinates is something that we already have seen. By default, if I think we used it before on a data set with points, and then it's a bit, yeah, more straightforward what it does, because every point has just an x and y coordinate, so the inputs, like the original data frame and the resulting data frame, have like the same structure. What you see here for a line string is that, yeah, you also get the coordinates, but every line string has multiple xy pairs, so it will also have multiple rows in the end results. And you see the index is still the original index, but then now repeated. It's kind of the reverse of the passing the indices here to shapely line strings. So this is doing the reverse, because maybe you want access to the actual coordinates. So that's what the get coordinates is doing. And you have also, like there is an additional function that you, keyword that you can specify. I'm not only want like the index for my original line string, but I also want to have an index within my line string. Like each part, like what's the order within that part, in case that would be useful. So that the get coordinates is, yeah, the fastest way to get all the coordinates out of your data frame. In the past, you might have like, again, did a loop through your geometries, and a shapely geometry had a chords attribute, which you could convert to a numpy array. You could stack that, but again, that's now, yeah, I don't know how. Yeah, it's again more than 10 times faster to use the method that is provided by GeoPandas. The last topic that was shown here is to end is also a new method in GeoPandas 1.0 related to, yeah, the title here is rounding coordinates. The problem with rounding is that, yeah, you can round your coordinates, and that's actually what we do here. It's like we apply, it's a bit complex, and it's not because we invented this, but I think Martin found it like on some Stack Overflow question, probably like someone actually doing this, using this way. So we convert to well-known text and then do a reg expression to get the values, round those, and then convert back, parse the resulting well-known text with the rounded replaced coordinates back to GeoPandas. Whole complicated way for rounding. You could, of course, now that we have these get coordinates, you could also get the coordinates, round them, and create back the line strings using what we saw before, like with the indices, because we have those indices in the output. So that's the better way. So this was the do not use this. You can actually get coordinates and round them and recreate the line strings or whatever geometry. But the problem with doing that manually is still that you're just naively rounding coordinates and nothing, yeah, we should probably add an example here, but nothing, if you just round your coordinates, ensures that the result of rounding that will still be a valid polygon, or because the rounding of coordinates, essentially you snap them to a certain grid by rounding, but that can introduce all kinds of irregularities in your structure of your line string or polygon. And so the better way if you do want to reduce the precision of your coordinates, there is a set precision method, again from Shapely, but exposed in GeoPandas. So you can take your geometry column and you can, for example, say I want to have a precision of like essentially the grid that I snap to needs to have a precision of, in this case, 0.001. And then you will see that I can show the original one as well. We limit the display up to 5 coordinate values, but actually it goes further. I'm not sure if I take an element out of it. It might be that Shapely nowadays also limits it. No, it's or text. Yeah, you see here like lots of numbers there, but so the set precision, in this case limits it to 3 values after the decimal, and so this will do an effort of keeping your geometries valid while reducing the dimension, the precision. It's not always like there are multiple ways. There is actually a keyword about how to do that. So there is the default is to ensure that the result is always valid, but there are also some other, like sometimes, if you have a polygon and you have like a very narrow piece that might be collapsed to a line. So do you keep those lines or do you remove those parts to just have a polygon in the end? So there are a few different ways that you can go about that, but that's a set precision is also a new method in GeoPandas 1.0 directly on the data frame to reduce precision. Some final questions.
It appears that Shapely 2 supports curved geometry. Is that true?
There was support added to Geos in the upcoming release of Geos 3.13. So 3.12 is the current release that is out. So it has been merged into the main branch. Some support for curved geometries, but as far as I know, what I don't know is to what extent they are already supported in lots of operations. I know there has been initial support to represent curved geometries, but I don't know how ready it is. That I don't know.
For the get coordinates function, how does it handle a multi-line string? Do you get a nested index, or?
Do you know? It would be nice, but I'm not entirely sure we do that. The thing is that if you have Shapely here.
I remember we don't do that. You get if you do index parts, you get each multi-line string as a single thing. But if you explode first and keep the multi-index and then call get coordinates to keep the parts, you get what you are looking for.
Like that. Let me quickly create an example. So I have a multi-line string. I put that in a geo series. So of course only one, but so we had get coordinates. Yeah, so that's just within the parent geometry. What Martin was saying is that you can explode first with index parts as well. So now we have, the original index, the index into the parts, and then the index within the parts. Of course, yeah, it depends a bit on the level of like the type of geometry that you have, what you need there. There are also, specifically for this, if you want to like the lower level handling, there is actually in what we use under the hood here are a bunch of functions from Shapely, and you can get like get parts from Shapely, where if I pass like the get parts function of Shapely will essentially every multi-part geometry explode that, and here you can ask to return an index, and then because for a polygon, because here now we have line string, but for polygons you could even have like yeah, you have like multi-polygons. So first already polygons, and then the polygon have an exterior and holes, and so you can I'm not sure if you do explode on polygons to give you rings. That I don't think so. So at that point, if you want to get the individual rings of polygons, then you need to use this Shapely function. So you could first get the parts of the multi-polygon, and then you have get rings for polygons where the first ring is the exterior and the next rings are interiors, and all of those have like a return index that you can set to true, and so that way you can get like all the indices. There is actually also, if you because that becomes very similar as this function, like it's not exactly the same because it are not indices but it are offsets, but this two-racked array, what this does is it returns you the same result as like the array with all the coordinates. So that's the same as what we have here above. But the additional values that you see here are not the indices. Like here we have like index 0 and then 0, 0, 1, 1. But what this does is essentially it says like in the coordinates here from 0 to 2, it's like from element 0 up to 2. So the first two rows is the first ring, and then from offset 2 to offset 4, or index 2 to index 4 is the second ring, and then if you combine those different things, like then again like from 0 to 2 are then the multi-line string. So the difference, if you use those index parts or in Shapely return index, you can, yeah, indices, while here you get like offsets. So it's a slightly different way to express the structure of the original data.
And I think that our time is up. If you have any questions, feel free to just find us somewhere around during the next 3 days. We will also be speaking about GeoPandas 1.0 tomorrow morning, the first, I think, talk at 9, so wake up, please. And yeah, I think that's all from us. Thank you.